First, let me thank the scientific committee for having accepted this talk. So this presentation illustrates part of the activities at APC that deal with the detection of the galactic binaries. The focus here is to discuss, as a function of frequency and duration of observation, how many sources may be identified and how it is possible to evaluate the confusion noise that results from their subtraction. So our galaxy is thought to have more than 30 million compact binaries emitting in the LISA waveband. A few tens of thousands could be individually identified by LISA between 1 and 10 millihertz. The remaining will form a confusion noise whose statistical properties are considered to be Gaussian. Now, independently of how the individual binaries are subtracted, whether sequentially or simultaneously, a question arises on when to stop extracting sources. That is to say, when the new sources that are added to the catalog have little chance to correspond to real existing sources. In this presentation, we try to contribute to this discussion by using a number of statistical tests to study the properties of the residual noise as a function of the number of subtracted sources. Now, the literature contains a variety of tests that studies the Gaussianity of a given distribution. Among those, we have used the following: the Kolmogorov, the Anderson test, the Grab outlier estimator, and we're in the process of looking at the Shapiro test. The first two tests do not give a yes or no answer to the question, is the distribution Gaussian, but rather a probability of the non-Gaussianity of the distribution. The third test gives the number of outliers to a Gaussian distribution, based on the assumption that the distribution is Gaussian with a given probability. Here we're using 95%. Now, before applying these tests to the physics, we would like to use them on some simulated data. So here we are considering distributions made of 10,000 samples obtained with a Gaussian random generator. We have generated 1,000 such distributions, and the Gaussian tests were applied to each so as to produce the histogram below. On the left, we see the statistics of the Kolmogorov p-value, and we see that most of the events corresponding to these 1,000 distributions correspond to p-value superior to 0.2, and we'll keep in mind this value for the future slides. In the middle, we look at the Anderson test, and here the Anderson statistics tells us that most of the pure Gaussian distributions have a statistic less than 1. On the right, the Grab outliers study tells us that in case of pure Gaussian distribution, it is rare to have most of the distribution will have less than 10 outliers. So the results of these tests is never a yes or no answer, but rather a number that has to be compared to a predefined accepted value. Let's note that even with pure distributions, the return values of these tests span a wide range. Now we can look at the physics, and here the physics for us is galactic binaries between 3 and 3.1 millihertz. In the Radler and LISA data challenge dataset, there are 900 sources in this frequency range. We have considered an observation time of 2 years in these examples, and the sources were subtracted sequentially based on their observed decreasing TDI amplitudes. Now, for the 2-year observation time, a total of 500 sources were subtracted, but only 422 were needed to reach a stable Kolmogorov p-value superior to 0.2, as was mentioned in the previous slide. So here we show above, in blue, the data corresponding to the TDI-A before any subtraction. So we see a number of clear spikes indicating the presence of sources with rather high SNR. Once we subtract the 422 sources, then we end up with the red distribution that has obviously a much smoother behavior. We can compare this red distribution with the yellow distribution below, which represents the TDI noise, instrumental noise only. And here we see that the red distribution has a mean level above the yellow one, indicating that we are indeed in presence of a confusion noise due to the galactic binaries. We can look a little bit more in detail. The data that we've been looking at is made of the output, the complex output of TDI-A. It has around 12,000 data points and between 3 and 3.1 millihertz, corresponding to a two-year observation period. Now, on the graph below on the left, we represent in black the distribution of these TDI strains with before the subtraction. In blue, we see the distribution after the subtraction, and the red line shows the sort of fit with the Gaussian function. The red distribution indicates the distribution of the instrumental noise. On the right-hand side, we are looking at the evolution of the Kolmogorov p-value as a function of subtracted sources. Initially, before subtracting any source, the p-value is extremely small, but as the number of subtracted sources increase, then we see a slow rise where we cross the value of 0.2 that we adopted for our test, and eventually, as the number of subtracted sources increase, we reach higher value for the p-value. So that is meant to indicate that already for a value of 0.2, the blue distribution function here is a well-behaved Gaussian. Now, once we have this, we can correlate the statistics of the other test to the p-value of the Kolmogorov test. And this is shown in different graphs here. On the left, we have the AD statistics, Anderson statistics, as a function of the Kolmogorov p-value. And we see a behavior that is reproduced on all of these plots. We start with high values for the statistics. We decrease very rapidly, and then we end up with a sort of plateau. And we have indicated here the criteria that we've adopted to call the spectrum Gaussian. Same thing with the grab outliers. We begin with a number of around a few hundred grab outliers. We rapidly diminish until we have less than 10, and then we reach a plateau when we have just a few, and we saw that that was significative of Gaussianity. We can look also at the SNR of the subtracted sources. Initially, we have very high SNR. Rapidly, this SNR diminishes as a function of the p-value or the number of subtracted sources. And then we reach a plateau, which is here around between 10 and 20, SNR between 10 and 20. We can look at the various parameters of this distribution, the mean value, the standard deviation, and the skewness. And they also show the same kind of behavior as a function of the p-value. The correlation starts with high value, diminishes very rapidly, and then reaches a plateau in all these cases, particularly the skewness. So the question here is the following. Could a combination of these tests be used to define when a Gaussian confusion noise is reached? Our summary. The literature provides a number of methods to test the Gaussianity of a given distribution. We have applied some of these methods to the Radler set of galactic binaries. Using a somewhat arbitrary value, 0.2 of the Kolmogorov Smirnov p-value, we have extracted a number of sources and evaluated the level of the confusion noise around 3 millihertz. Note that we have done similar studies at other frequencies and for other observation times. Now some remarks. As we've stated before, the evolution of a non-Gaussian distribution to a Gaussian distribution is a continuous process. It may be interesting for the consortium to have a discussion on the best criteria to adopt in order to define when the Gaussian confusion noise is reached. It would also seem necessary to study the quality of the extracted source parameters as a function of this criteria. How far can we dig into the noise before the quality of source extraction becomes irrelevant? And another question that I've also been asking is the following: is the SNR the only necessary parameter to control the subtraction of the sources? On this, I thank you very much for your attention.